Howdy, howdy. I'm Carlos, and every week I get together with some friends to talk about AGI and related issues like how evolution works. So this week we talk about a question. Could evolution by natural selection produce an advanced fighter jet like the F-22 Raptor, which is full of titanium and steel and exotic materials? Could human engineers design DNA that would grow into such a plane? Or could they design DNA that would grow into an organism that would then go on to build such a plane, the way a bird builds a nest? That is encoded in genes, by the way. So we discuss those and other related questions in this episode. But with that, please enjoy. The game Baba Is You, which is this phone game. And I remember playing this game where you kind of assemble blocks, and it's a very simple mechanic. But the blocks, you compose them and they produce different behaviors. So if you say like Baba is, water, then like you turn into water, let's say, or whatever. Like, so and then you have to combine these to solve the puzzle. And this game, sort of like with chess puzzles, it's interesting that like you can be so close to having the solution. You can see all the pieces on the board, all the things that you could touch and mess with. And yet you can be just ever so slightly out of order in your steps, so that you don't have the solution, you don't see the solution, you don't know how close the solution is, and then somebody comes along and says, "Oh no, you have to do the knight first, or you have to move this block here, there," and then it's done, and you're like, "Oh, that's so simple and easy," and then you forget that you were like, I have no clue. I battered my, and sometimes with these games, less so for chess, but for this Baba Is You game, I would play it and I would like spend a while, enough to get frustrated maybe a little bit, or just, out of ideas on something. And then I'm like, screw this game. And then come back months later and try the level, and there's like, oh, what if I do this? And then it's solved. And you're like, interesting that I didn't see that before. And I wonder why it is. And interesting that, something changed. But
I know that game.
Yeah, it's a cool game.
I've played it. Yeah, it's like you have levels, and they shift every level. Like there's different rules or something like that. And it's like logical puzzles, but you need to understand the logic of the puzzle. And I think it varies from level to level. I played it a long time ago, so I don't really recall. Do I get it right?
You should have put it in your space repetition, all the levels.
Yeah,
Paul is an aficionado of a space repetition, for anyone who doesn't know.
That's true.
Yeah.
Space repetition is great, yeah.
Yeah. What I most like about this, by the way, as an illustration of problem solving, is that it is much more of this categorical type problem solving, and it's discrete. And I find again and again and again that sort of the tension between the discrete and the continuous comes up. And this is a great example of that, because it's one where there are discrete options, and you can move this particular block to this particular spot or not. And the gradient, at least in this particular space, there's not really any sense in talking about gradients. Maybe you have gradients in some other model, trained in some other way. But as far as like this particular situation, it's so discrete. They're just like, I don't feel like I'm edging my way towards a solution. I feel like I do not see it at all. And then at some later point, I may see it. And okay, there we go. So there's a different lost landscape. So I think that one could spin that up into a deeper kind of illustration of different domains of problem solving, the different needs of those different situations. And maybe one could be skeptical and say, hey, you can just train a bigger neural network according, in the usual way. And if it's smart enough, it can handle it. It's not like StarCraft or some of these other games don't have elements of discreteness to them. And still they can, in some sense, be solved with the right approach. So one wonders.
Yeah, I mean, isn't discreteness just a threshold that is sort of imposed on the continuous landscape, where once the threshold is being met, then the next discrete step has happened?
Say that again?
Isn't the discreteness just a threshold that is being defined as once X has happened, then you're there? But that does not, just because there is this discrete threshold, which is useful to evaluate progress or whatever, it doesn't mean that the underlying dynamics are discrete.
Yeah, there's an interesting thing where you could say, hey, I have this very discrete set of options, and I don't know how to make a neural network handle all those elegantly. So what I might do is I'll just approximate it with some kind of simpler or a more continuous surface that is easy to navigate. And I'll just sort of smooth out the system in the hopes that I can now navigate that system easily and then transfer the result back to the original system, which is more discrete and hard to navigate. And if you do that job well, if the situation allows that kind of inventing of a proxy that is easy, and then you go back to the original, then that's great. But there's always this question of, if I'm going to not solve the problem directly, but solve a subproblem or a variant of the problem that is easier, there's always the question of what is the mapping between these problems, and does it in fact help you to solve this other problem that's easier, and then go back to the original hard problem. In general, it probably won't be the case that there is always some simpler thing that you already know about, and I'll just like always apply this heuristic to make the problem easy. But anyway, I feel like this is like an interesting test case to think about with some of these more discrete games. And maybe I'm just like, maybe Ali can jump in with like a sanity check here, because I don't train neural networks for a living. So to me, this seems like, a difficult thing. But maybe given the history of game playing AIs, this is not at all an interesting test case where it's just you train it the normal way and it's fine.
I'm sorry, what was the question again? What is easy versus difficult when training neural networks?
Just like a game where the choices are discrete, like in this Baba is You game, or like a chess puzzle.
Yeah. I mean, the context I can add there is like, when the game is discrete, in again, machine terminology, we'll say the reward is sparse. So like you only get a reward at the very end when you do everything right in order. So that is definitely harder to learn. And you need to rely on some more fancy tricks or more advanced techniques, as opposed to games where you constantly get points for doing the right thing, even if just a few things.
I think that there might be maybe a degree of discreteness there, or like a distance from the result and that kind of thing. How indirect?
Yeah, it's not the same thing. Yeah.
Ultimately, as David Deutsch points out in The Beginning of Infinity at one point, you can model continuous things with discrete things and
Right.
and this sort of thing. So, at some point, the difference doesn't maybe matter that much. But yeah, when there's these like very large steps that are hard to model in some continuous sense, where you're just like, hill climbing is one kind of thing, and stair stepping with sufficiently small stairs looks the same, but with really big stairs, it doesn't. And so different tools are required. Yeah. But anyway, that's not the main thing I wanted to talk about today. The main thing is that I went viral, for my definition of viral anyway, for talking about this post about the F-22 fighter plane. And there was just a cool video from Massimo on Twitter, who posts cool videos all the time. And this one covered, it was just a really cool slow motion video of the F-22 Raptor. Cool fighter jet doing cool fighter jet things, engines and everything to it. And it was cool. And so I like, whenever I have an opportunity to like spin this into my own research spiel, I like to do that. And in this case, what struck me was the idea that look at this advanced human-made object, and I'm always asking the question: could an AI do that, or could evolution do that? And so, with any kind of creative process, I think you can ask the question: hey, here's a thing, here's a creative process. Could that process make that thing? And you can really ask the two different questions. One of them is like, could it make it at all? And the other is, should we really expect it to, or like, how easy is it for this process to make that thing? Because you could say monkeys at typewriters can do Shakespeare. They could. That's one question. But then also, should you expect that? The answer is no, because there are different reasons for that. One of them being the efficiency of how you navigate the space of words to produce a particular result. And monkeys don't do that particularly efficiently. So there are different kinds of questions you can ask about a system, a result, and whether that system can produce the result, and how easily or with what confidence, or these kinds of questions. And so when I saw that post about the F-22, cool fighter jet, I'm asking the question: what kind of thing does it take to produce that, or to produce it reliably, or to produce it efficiently, both to discover how to make it and then actually make it? And so my take on that at the time was sort of like, yeah, evolution couldn't do that even in 10 trillion years. The primary reason being not that it's complex, because a cell is more complex than a plane, but that it requires trying things. And with evolution, every step along the way has to work. It has to survive and replicate. Whereas with human designs, you can make a design that doesn't work in any sense of work, other than it's an interesting stepping stone to the next design. And so you can put it in the folder, you can learn from that mistake, you can build on it and remember it. Whereas evolution doesn't have that luxury. Every step along the way has to work. Otherwise, it is destroyed and forgotten to time. So that's the feature that most distinguishes evolutionary processes from sort of the creative ones we're used to. And therefore, it can't produce things like the F-22. Now vibe to this.
Yeah, it's the difference of types of selection, right? So biological selection, as you said, has to be viable or it's dead. And when it's dead, you forget completely, like the genes are not remembered or stored. Whereas human evolution, or human knowledge creation rather, our selection process does not involve deleting and forgetting everything. We can select but still remember the stepping stone, or we can we can say that something is false, but it's a good approximation. So we have other reasons to keep information, even though we have selected against it. That's just a new standard for how we select things.
I think also one way of putting this into perspective is that you can take all the stuff that I said and summarize it as evolution is really constrained. And so as it goes about its search, you could imagine a search process which is more liberal, open-minded, open-ended, and so on, and more permissive in what kinds of paths it can take. Or you can imagine one that's more like a dictatorial parent who says, like, you're going to do the thing I said, and we're not talking about anything else. If you pick up a toy of the wrong color or something, like this is not okay. We're doing this today. And so you're going to cut off certain paths. And that's what evolution does. In particular, it says, if you can't survive alone, we're not going to take this forward. And so the general lesson to learn from that, I think, is that that is a sort of fixed filter. Evolution always demands this everywhere, that you survive and replicate. And so you can talk about the fact that it's fixed, but also that it's constraining. And so there's certain things that might lie outside those constraints that will be useful paths to take, but you can't take them. Evolution doesn't let you. And so I think at that level of abstraction, you can see, like, this is a way in which you can make evolution more constrained and therefore make it impossible to reach certain things for evolution. But in the human case, I have my own sort of personal notes on kind of how I do research and what ways my own thinking and research has sometimes gone wrong. And one of them, these notes, is called over-constrained to hell. Like if I just put too many constraints on myself for what I need to be working on or what I need to achieve or something. You can put so many constraints on yourself that it's difficult to find any good path forward. So it's sometimes removing some of those constraints allows you to say, okay, this doesn't have to be a paper. This doesn't have to be this. This doesn't have to be that. And that allows you more paths to explore further. And you are no longer stuck as a result.
Yes, it's very interesting. And I think there are many parallels also, even with the constrained neural network setups that we are using today, where we're introducing randomness to free optimization processes from this kind of trap of being stuck locally, in somehow a locally constrained environment. And I think very similarly about my own thinking and my own constraints. Like sometimes you just gotta reset, right? Maybe sometimes you just gotta get up and take a walk and completely leave the physical environment that you're in while you were thinking about something. And suddenly that removes some constraints, right? And it's completely orthogonal to the actual thinking that you were doing. But somehow it has these trickle down effects and resets potential constraints that have been maybe implicit or unconscious that then get unblocked.
Yeah. I think I'm just mostly interested in the mechanics of search. And so whenever there's a mechanic that's kind of general, it's just interesting. And obviously a search which never tried anything couldn't find much if it was just a fixed point. If it was a fixed loop, that wouldn't be good. And likewise, if the paths are constrained in some way, this is a tricky thing because, I was just saying it's bad if you're over-constrained. But this hits upon attention, which is, I think, an important thing in all search processes, which is if you want to be successful in a search, you either need to, the part of that is about being efficient. And there are kind of like two ways you might think of to achieve efficiency. One of them is to like make the search space really narrow. Like there's only 10 possible searches. So you can just go through all of them individually and that's fine. But once the search space becomes really large, you can no longer just go exhaustively through all of them. So, so if you were to leave it at that, hey, I have a big search space, just try iterating through all of them. Your search would probably not work very well. So you enlarge the search space, which is in one sense a good thing because new good possibilities are in your search space. You can now reach them. Hey, that's great. But now it's such a morass, it's such a large haystack to search through that in practice you find nothing. So that's not good. So you sort of, as you enlarge the search space, you need to enlarge or improve your ability to navigate it, to constrain yourself in sort of an intentional, self-inflicted kind of way. Like, okay, now the world doesn't force you to a small search space. It says you can do lots of things. But now you yourself have to invent the right constraints to navigate it efficiently and say, okay, well, the world won't let me do any of a million things, but I'm going to try this particular filter now to direct my thinking. And you need some kind of direction. Otherwise, you would be lost in that large space. So there's this always tension of enlarging the search space, bringing more possibilities to be reachable, but then also having those right filters. So you can take small, narrow, efficient paths in that space.
This makes me think a little bit about another aspect, which you've talked about a lot, attention, of course. Biological evolution doesn't have attention. There's nothing that can direct which genes are going to mutate and, cause a particular effect. Whereas human knowledge creation, we do have some limited form of attention. I mean, it's not that limited, but we have some form of attention. Like we can determine which theories we want to vary. We can't determine how we vary it or, if it's going to reliably produce a good result, but we can intentionally vary certain theories. So that's another one of the big reasons why human evolution is a bit better than the biological evolution. And that, I think that has a lot to do with the search space as you're talking about, right? The search space is just kind of fully open-ended, I guess, and random for biology, but we can narrow it ourselves temporarily, and it's pretty much all open-ended. We can narrow it for a while, we can open it back up, we can narrow it, and so on.
I often like to think of search processes as like, on the one hand, you have a source of craziness, novelty, generation, recombination, and that's almost like a water spout or like a shower thing, and so that's diverging stuff. And then underneath that, you put various kinds of sieves and filters, and you can put in some and remove some, and so yeah, you have these two pieces you get to play with. The thing that generates random stuff, that's like the falling rain of possibilities or things you can think of new potential solutions to something. And then, yeah, you have the filters below it. And with that picture in mind, you can ask questions like, you can try to think of any given search process, whether that's neural network training or learning or scientific discovery, as this model of the spout producing the raindrops and then the filters underneath it. And you can begin asking questions like, in this particular system, in evolution or whatever else, are these two components fixed, for instance? Or can they be changed? Are they changing over time, maybe? In evolution, just as the solar system is forming and changing and so on, and the temperature of Earth is changing and so on. And so all the survival requirements and the selection pressures are changing, even apart from any other predators. Just like temperature of the Earth is changing. So you have to handle that. So that's changing the filters on what can survive. And in the human case, it's even more advanced, where you're just like, I can rip out some filters and put in some new ones, and I can even invent some new ones that have never existed before, and I can slide those into the process. And then I could say, hey, this thing here is to what could you say? I have too many filters in place. So I'm going to remove one of them because that's over constraining the process, and nothing, no water is reaching the bottom of the system. Nothing's coming out. So I need to remove some filters and say, let's take it easy here. And so on and so forth. Or you can ask about the top part of the system, producing the raindrops. You have the different kinds of faucets or different kinds of sources of fluids to put in there. So I think it's a helpful and concrete kind of model.
Yeah, I like it.
I think it's kind of.
Oh, please, Sebastian.
Right. I just realized again how crazy it is that, this whole process that we just discussed with our knowledge evolution is so conditional on the culture that we have created in the last couple of centuries. And like all this other time, we would have been potentially able to have this accelerated knowledge discovery. But we weren't even faster for the most part than biological evolution, even though we could have been.
Yeah, tragic, unfortunate history.
Yes.
This kind of hits upon the idea of having a system which has like a lot of power that is going unused. And that's interesting. And a lot of the things that I think about with regard to AGI one of the ways that there's a tie-in to that historical change from like not making progress to making progress, despite the fact we could have made the progress the whole time, is that when I'm thinking about AGI, you have to sort of maybe separate out questions of like scientific method and so on, because like you can have an AGI system that isn't making scientific progress. Like that's not part of the stuff that's built into it. However, having said that, one of the things that it does need to be able to do, arguably, is like learn a particular culture. And so even if like adults in a culture aren't making progress, all the children are making progress and learning the stuff that culture already knows, including how to keep itself the same and not make any further progress beyond, just how do we eat, how do we survive, etc. And I guess that's what David Deutsch likes to say about like why we evolved to be the way that we are. Like it turns out that learning a culture is the same problem as learning what the world is like. Mm-hmm. Or at least it involves this process of conjecture and criticism and trying some stuff and filtering out the things. That basic machinery is the same. And I guess like another way to put that is that guessing what someone else means when they talk to you, like if we're having a conversation and you're telling me something, you're spitting out these syllables. Like me guessing what you mean is a hard problem. And there's a lot of things you could mean. And the task of communication is for me to like say, hey, he could potentially mean any of these 10 trillion things, but I think he means this. And so when you say, there are 5 dogs out there, I have to, in my head, distinguish that from like, there are 4 dogs out there. There are 4 cats out there. There are 4 dogs in here. Like those are all other things you could mean, including, and many other things unrelated to dogs or cats, or whatever. So I have to correctly specify which of those things you mean somehow. And so that task is a little bit like saying, there are lots of ways the world could be. Which way is it? I have to, again, take all these possibilities, narrow them down, and so on.
Speaking of trying to figure out what someone means when they're saying something, I was looking at the post interactions for your tweet that went viral, and there's a good chunk of people who are basically just saying like, oh, but evolution did produce an F-22 Raptor already, like whatever happened is just some evolution, and therefore your tweet is like wrong or whatever. And I just find it interesting because I read the tweet just now and it's pretty clear the distinction you're making. So they also just, it's not just a semantic thing. They didn't understand the distinction that you were trying to point out about every variant or every increment has to survive and reproduce. And that is a different thing from not say natural evolution, or maybe we should call it Darwinian evolution, and that this human evolution thing is a separate process. But yeah, I just thought that was interesting.
It's incredibly interesting because despite me having had all these calls and all this distinction, and so my brain neural network being trained on how to separate the two, it was the first immediate thought that I got when you posed the question, right? I immediately knew well, that's the wrong thought, right? We are like separating the problem differently here, and so on and so forth. But it seems to be like the first thing that comes to mind for potentially other people as well.
Yeah, let me pull up some of the replies. Let's see. Yeah, so one of the things I think is interesting is about somebody actually replied and they said, evolution is actually much more general than just what biology is up to. I thought, oh, like you're actually hitting upon exactly my whole thing, which is like, yeah, there's this process of variation and selection that's happening far beyond just what is happening with genes. It's happening in human minds, it's happening with neural networks. Anywhere there's progress, there has to be the trying of new things and the keeping of what works. Like there's no escaping that. And like even in places where there isn't progress, like things are just changing. And some patterns are sticking around and some are not. That's happening. And, sand on the beach, it's happening with atoms in space. Stuff is changing and, you're seeing some patterns stick around and other ones not. So it was cool to see that some people were like, hey, this guy has it wrong. But it was actually just like a terminological thing. Like I'm saying evolution, but somebody is saying, hey, I think we should have a broader definition of evolution. To which I am like, yeah, exactly. We are all the same religion. But
when you start having this broader definition, then we can say like, particles just kind of mashing around at each other will eventually come to life, and then life can create lots of things. So would it be appropriate to say that, particles bashing around at each other can produce life or can produce the things that life produces? Or is there a reason to have like a hard distinction between the processes of particles just colliding and the processes of biological knowledge creation?
Well, one thing you can say is that evolution doesn't necessarily involve knowledge. Cumulative evolution does. And so it's one thing to say we have produced a new thing. So you can like separate out maybe a couple different things. One of them is like I have some stuff and I have combined it to make a new thing. Mm-hmm. Cool. So that's something important. However, if it's immediately destroyed, obviously that's not going to be built upon, and you're not going to have the emergence of much complexity because every time anything happens, it gets immediately destroyed. So you're not going to see a complex organism as a result. But if you like look at into intergalactic space or something, you're going to see molecules maybe occasionally combining and whatever. So you have energy, you have things, you have change. So that's one part of it, but it's not everything that you need to see things like us emerge in the world. And then, you have like natural selection. Like there's no way of getting away from the fact that like some things will be preferentially, will continue to exist and other ones will not. Again, that's just going to be a ubiquitous thing. What's special about our planet is that, somehow you got information stored in such a way that it could then be used and affect the world. And that like more information can keep getting added to the system. And so every time there's like a new adaptation that would be useful, it can actually be saved. So it's like the game of life finally got a hard drive, and that turns out to be super important. If you have to start from scratch every time, you won't get very far. So I think it is fun to kind of like dig into all these pieces and see like, because traditionally when you hear about evolution, it's going to be like in the context of like a religious debate or something, maybe if it's like in the public sphere, or it's going to be about the mechanics of DNA molecules. There's lots of ways to think about this stuff. And some ways are quite common, but I think it's fun to think about it from this more high level view where you just say, hey, let's just like take a look at this at the most abstract perspective and see like, ask questions like, what if you just entirely remove one part of the evolutionary process? What if there are no genes? What if there is no hard drive, no means of storing information? What happens then? What if there's no energy in the universe and there's just nothing can change anymore? What happens then? What if there's no natural selection and just like everything that can happen does happen and no such thing as like survival, like nothing gets killed. Like you just think if it's formed somehow, it sticks around and just continues producing new generations. Like you can do that in a computer. You can just be like, I'm going to make some stuff, and for every single thing that I make, I'm going to make 10 more things derived from that. Like there's nothing saying that you have to select anything. accept the fact that like you're going to run out of resources eventually if you do that, and then the whole simulation stops. But in a world with infinite resources, you could just say, hey, I'm going to try something new, and I'm going to keep trying 10 new things for each of those, on and on and on and on. That's a valid, logical thing that could happen. And you could ask what that would look like. So I think that's kind of a fun lens on evolution that I haven't seen too much elsewhere.
Mhm.
I'm going through my replies here. After that.
Are you surprised that people in the replies are saying these things with the broader definition of evolution and so on? I feel like they just read Dawkins and then so the ideas are familiar and so on.
That was a rare response. I only saw one person say, hey, evolution is more general than just biology. I feel like it's a very elevated take, if I do so myself. But I think, in that case, what's interesting is to say that if you're going to look at evolution in this more general way, there are really two things you need to do. First is to recognize the unification of all these evolutionary processes and say, hey, there is a more general phenomenon here, whatever you want to call it, of variation and selection. Like that is true, that is everywhere, that's in minds, it's in genes, it's everywhere. But then there's a second step, which is to say, but they're all extraordinarily different. Why is that? What are they doing differently in the way that they perform variation and selection? That then becomes the super interesting question. And it's, once you have recognized that they're all the same and they all engage in variation and selection, that's a very useful stepping stone to saying, okay, now I can more precisely ask how they're different. Because I'm not going to be too obsessed with or distracted by the superficial details, that this one happens to involve chemical molecules and this one happens to involve hard drives or whatever. I'm going to recognize that those details don't matter. What matters is the variation and selection. So you have this new lens to more carefully analyze the differences. But I think those two things go together. Recognize the unity and then dig into the differences. Yeah, can a bird build an F-22? Well, one of the things that came up, by the way, in the thread was that if you ask, could evolution produce an F-22? There are a whole bunch of reasons, by the way, where it's just because it's like made of metal and things like that, and it doesn't self-reproduce. F-22 has no uterus or whatever. Like there are these kinds of objections you can raise. But then again, evolution can make use of metals. I think certain organisms have that. But even beyond that, one of the also objections was like rotating machinery is quite hard for evolution to produce because you kind of, you want to get blood everywhere, you want to get nerves everywhere. And it's kind of hard to like do that. It's tricky. Like if you think about how to do that as an engineer, like it's not totally obvious how you make that all work properly. And so there are reasons why you could say that's quite difficult. But that's all beside the point, because if you want to talk about evolution and what it can produce nests, so you don't have to have it be part of the body for it to be guided by evolution. Genes, and this is one of Dawkins' big points in the extended phenotype, genes can make bodies, but ultimately genes are just there to improve their own replication potential, to reproduce themselves. So if they make a bird not only build a body, but also build a nest, that helps the genes carry on and replicate. So why not have the genes make a bird that builds an F-22 and institutes nuclear deterrence and so on? That would also maybe help its replication success. So even if it involves exotic metals that can't be incorporated into a chemical system, you can still say, I'm going to build a nest. And I'm going to make a wrench that I can hold on to build a machine that can lift a huge thing, that can do that, because we already do that. Humans are in existence proof that biology can control metals and everything else.
So why aren't we considered that bird?
Say again?
Why are we not considered that bird that biology uses to create the F-22?
Oh, yeah. In that case, that's the key question, which is, okay, where is the knowledge to make the F-22? Because the knowledge to build a nest is in the bird's DNA already. The knowledge to build an F-22 is only in human minds. Evolution produces our general intelligence, but it doesn't tell us how to build any particular thing. So that's the difference. So the thought experiment here is, could you have a genome where the instructions to build the F-22 are already in the genome. They're not discovered later by the mind that is specified by the genes. They're specified in the genes themselves. So, and David Deutsch brings this up in the beginning of Infinity at one point. He says, one of the key things about DNA is that like it's very much like the human mind in the sense that like for a long time it didn't do that much that was complicated. It did fairly simple things for most of its history, and then later, much later, it exploded in terms of the diversity of organisms that it specified. So when humans could initially, there was a period in history where humans could have thought many things, but they didn't. And then much later they did. And there was also a period in history where the DNA could have specified many types of organisms, but it didn't. But then eventually it did. So in both of these cases, there's this enormous power in the system that goes undiscovered, unexploited. And Deutsch asked the question, okay, DNA didn't do that much. It made individual cells. Then it exploded, made all these much more diverse organisms. How much further can it go? Could you build in the instructions not only for one cell, not only for multi-cell, not only for birds, but also for intergalactic spaceships? Is it obvious that that cannot be put into the DNA, such that you would build, you would put that cell or that DNA into a cell, and it would make a bird, and then the bird would do this and do that and do that, and it would eventually produce, via whatever sequence of steps, a galactic spaceship. And then, so there's that question. Could DNA as a molecule contain that relevant information and all the building steps it required? And there's a separate question, which is, could that evolve? Is evolution capable of figuring out that quite exotic sequence?
Yeah, so it seems like you could ask the question, or not the question, but the statement that you made that the F-22 could not be created by evolution. I don't remember how you put it exactly, but you can restate it in two different ways. And one of them is, can the F-22 be encoded in DNA, or the instructions to create a F-22 be encoded in DNA? Which the answer is yes, right? And then the other question is, can it be created with variation and selection using a limited process of selection and no attention, something like that.
Yeah.
So the other question is, can there be evolutionary pressure? Like, can it be like out of the whole space of different things that someone could have done through random variation, could have encoded into the next offspring? Like, can this even be meaningful, right?
Mm-hmm.
Yeah, questions about DNA are really questions about knowledge representation, and like, do you have a representation which can encode a particular idea? And then, if you have a Turing complete representation or something, then that's kind of the top shelf, I suppose. Although you could have a shitty programming language that's Turing complete, and it just is hard to specify useful things in it. So there are questions about, could it represent it? Could it represent it in a particularly efficient or useful way? And then the separate questions about, assuming you have a knowledge representation which can encode the things you care about, do you have a process which can discover that?
I've got a question about some of those, like the distinctions that we're making here. Is there a factor of something needing to be reliably created? Like, let's just say, I don't know if this is true, but let's just say humans are reliable at coming to the knowledge to create an F-22, and biology wouldn't be reliable at it, but it could. And the same for just random particles, disembodied on Mars. It could just randomly construct an F-22, but it's so unreliable that we just might as well say it's not possible. Is there some aspect of reliability that's a relevant thing here?
Well, one trick of that is that there's no reason for humans to make an F-22 if the right selection pressures aren't there. Like, you only want to make that when you need that. So that's one kind of question. So I guess if you held that constant and you said, hey, let's have the same sequence of historical pressures, let's say that would be useful, would you come up with that? Yeah, I don't know. I mean, there were competing visions of what should be built for that role. But yeah, I think that's more of a question about convergence and like, do we have an error correction process which will converge on the truth? And I suppose there's a variant of that question about evolution, which is like, famously, I think Gould said, if you reran evolution from the beginning, it wouldn't have produced what it in fact produced in our case. Like if you reran the simulation and you ran the process, it would come up with a lot of stuff, but probably not the same stuff.
Right. So this is what the reason why I asked this is because we say that, well, the phrase that was used is that we have the capability, or like, biology has the capability to have to encode people who have, Turing complete minds or whatever the heck. And then people have the capability to create any processes. So that the statement of that we have the capability, but we haven't used it yet, it seems very equivalent to, humans could have made the F-22, but they haven't yet. And then the way that I'm interpreting that is just that it must be, there's a point in time where we would reliably come to the same type of thing. And, if we rerun all of biology, then all of evolution, it wouldn't be reliably coming back to this point. So anyway, you can untangle my confusion from all that, hopefully.
Yeah. I think it's interesting to say, like, if you put human type minds in possession of all the knowledge that people had when the F-22 was designed, would they eventually come up with that kind of thing? I think the answer is probably yeah. Like, there were lots of debates happening. There were lots of people that knew the relevant technology and engineering, and like there was no world in which people would decide like not to put wings on it. Like you could make a rocket, but that's a different thing. It wouldn't have the same characteristics, fuel efficiency, and this and that. So like, okay, there's one aspect of the design that you're pretty sure people with any engineering skill would hit upon that aspect. And on down the line, you could go and say, would they be able to make these decisions? Would they have the right knowledge? And would they be able to deploy it and recall it at the right time? Questions like that. Or was it just a lucky shot? Like if you looked at the history, it's like one guy put a bucket of books together and ripped out 10 pages. And then he's like, guys, let's build this. And it happened to work. But most of the time it wouldn't have. No, that isn't the history. It was a highly convergent history where they debated and settled on a design that worked. Yeah. And so what you would probably say is you wouldn't end up with precisely the same design down to the molecular level, but you would have a functionally equivalent design. And even if they made a mistake, it would be the kind of thing that would probably be corrected over the course of a couple generations of it. Although, having said that, if you were to think of like an alternative history, it might well be that you make a mistake in the design of one plane and then you never correct it because by the time you have another opportunity to say, what is the next military platform we want to build, things have moved on. And so you're just like, we're going to build crazy space lasers. That's the thing that matters now. So there's no point in trying to build a better plane.
Right. Or the mistake is just better than the original design that we were considering the original.
Yeah. It's kind of what happens like with Africa leapfrogging technology. It's just like, hey, like we're not going to go back and try to reproduce exactly the steps from before. We're just going to take the best thing now and exploit that. No need to build a bunch of power lines or phone lines. But yeah, let me see what other objections we had. I saw, by the way, that about 10% of the comments were just insults. So that's nice. Do you understand what the fuck stupidity you have just said?
What's your favorite insult? Please cite one.
Well, my favorite one wasn't actually, it was slightly insulting, but it was more about, let me see here. It had to do with rat fornication, I believe. So let me see if I can pull that one up.
Okay.
You can discuss that topic while I look for the
rat fornication. Let's just think about it.
Yeah.
Well, I wonder, do you understand how stupid what you said was?
Yeah, but yeah, I think it was just like saying one of the things that comes up whenever you talk about evolution versus human design is that some people want to emphasize that evolved designs have come about over billions of years and are very advanced and more advanced than anything humans have made. But like you can concede all that and say, hey, a cell is more complicated than an F-22, but that's not the point. The point is like there is actually a separate point from the one that I was thinking of, which is that not only can evolution not produce an F-22 because of those constraints, it's over-constrained, it can't take the path that is needed to get to an F-22, but also evolution's small steps lend itself to greater complexity and messiness, because an F-22 is built so that it doesn't have any extra parts that you can just tweak randomly and produce a slightly better design. Like human designs in general don't have that feature, and it's for good reason. I like to say that like a protein works because it has a certain shape. But proteins are like these big masses of molecules that are folded in just the right way and everything. But a bunch of those you could switch around and it wouldn't really affect very much. Like you just kind of have to put the right mud together. And at some point it has like a little cup holder, Mm-hmm. So it's just like, I need a big sphere of mud with a cup holder on the top. And that will be the design of the protein that has exactly the right functional shape for the body. It can grab onto the right thing and it can connect this to that. And okay, it does the job needed. But like there are 10 trillion ways to assemble a ball of mud out of small bits and bobs that has like a cup holder shaped thing at the top. So evolution can start tweaking that all the time. It's got many thousands of things it could tweak in that design potentially without disrupting the basic structure to make it slightly better. But that's not how we design, human things. The iPhone is in nowhere described as like a ball of mud with a certain shape on top.
Mm-hmm. Did you get any people accusing you of hubris or something of that nature?
I don't think people. I feel like hubris accusations are not very common. It's a rare word from the start, I think. So I think anybody who's...
The choice of word there is sort of a counter selection against even doing the insult. That's what you're saying, I guess, right?
Mm-hmm. Kind of. Anybody who accused me of hubris probably is themselves full of hubris for knowing the word.
Mm-hmm.
Yeah. Let me see. I'm currently hunting for this thing. Yeah, I think, let's see here. Yes. Okay, so I have found the rodent thing. Are you prepared?
Yes.
Let's see. Okay, so I have my thing, hey, evolution couldn't produce the F-22. And then they say humans could do better than evolution in terms of what we design. I'm paraphrasing here. But we currently do our processes of creativity worse than rodents randomly breeding each other in the woods. So they're saying a bunch of rats fucking is basically achieving more than human creativity, which I would object to. And so if you want to pause here like a chess puzzle and say, like, what would your response be? Okay, I'll just put up a hand, 5, 4, 3. And now you have your response in mind. My response was, I doubt that your response itself could have been produced by rodents randomly breeding each other in the woods. So I think there's some truth to that. Mm-hmm. I could be wrong. By the way, I always think like, I kind of quote tweeted that when I said, when you wake up in the morning, you really just never know what sort of sentences you'll be saying later. I doubt your response could have been produced by rodents randomly breeding each other in the woods. I had not planned that one. That was not part of the sentences I had chosen to speak that day.
Mm-hmm.
Yeah.
Great response, for sure.
On a separate note, by the way, I think there's more to talk about there potentially, but one thing I've been thinking about on a separate note has been the idea of generalization and reach, and this kind of stuff. One of the points that David Deutsch makes is that some ideas, like general relativity, reach into many places. They're universal, or they apply to lots of situations. And those are obviously very useful ideas, and you want those kinds of things. You don't want an idea, some ideas are very useful, but they're very narrow. Like my keys are on the table near the front door. You want to know that if you are the owner of those keys. But that's not going to tell you much about anything else. That's not the sort of thing that you'll get a Nobel Prize for. So we're interested in that kind of deep knowledge with many applications. And aside from just wanting something which applies very generally, you want something that tells you something new about the world, ideally. Because you can imagine a world where you have a lot of knowledge of the world and all you want to do is express it more effectively. And so you summarize it, you just compress what is a messy description of all your data, and you just compress it. And okay, that's nice if you can do it. But you could imagine two ways of doing that. One of which says, here's everything you know told to you more efficiently. Okay, that's nice. But what if I said, here's everything you know expressed in such a way that it also tells you things you didn't know? Or here's a thing which is consistent with all that you do know, or some of what you know. And again, it tells you something that you didn't know. That's what you would really like to have. So when it comes to thinking about the reach of an idea, you can just ask one question, which is, how many places does this apply? But another thing you could say is, what does this tell me that I didn't know already? Like, ideally, it would tell me a lot of things, only some of which I knew before. So I think that's one way of thinking about reach. And the important thing there is to ask, okay, what kind of processes would give you such ideas? What kind of things do you need to be thinking about in order to hit upon like relativity, which says, yeah, you have some data, it's consistent with all that, but also it tells you things you never guessed, like the existence of black holes. Because a mere summarization of what you know doesn't achieve that. And a mere curve fit of all your existing data doesn't achieve that necessarily. So that's something I've been thinking about.
I've been thinking a lot about Lamarckism, and I'm kind of trying to reformulate it into a general theory of knowledge. And the way that I think about it now is that there's knowledge already encoded in the environment, and the task of a person or whatever organism is, their task is to absorb the knowledge that's already encoded in the environment. And in that case, of course, there's nothing new. There's nothing possible to be new because you're just gathering information or knowledge that's already encoded in the environment. There's no possibility of creativity. Whereas, of course, with Darwinian knowledge growth, you can make something new. So I like this, the fact that you make that distinction of, the reach of an idea, but then also does it tell you something new? Is there any new thing that comes from that? Is it just, as I just said, is it just knowledge that's already encoded in the environment that you're copying?
Yeah. By the way, with like curve fits and data, like any rule like piece of knowledge will say something about unfamiliar circumstances. It's just generally not true at all. It's a hallucination. So some formats for expressing things don't do that. They're just a table of existing data. So that makes no statements outside the data. Whereas a curve fit, which is a function, and it can take in, I guess the formal thing would be what, like the domain of the function, like all the inputs you could possibly give it. Okay, so that would have, it could take in lots of things, including the things you've seen, but also things you haven't seen. And then you could see what it says about the things you haven't seen. And in general, those curve fits are just, useless outside of the data. So I think there's this general question of, what else do you need besides the data?
Right.
If you want to hit upon an idea that actually applies outside it.
And what more do you need? How do we do it?
Well, I guess the first thing you could say is like, do you need anything else? And that's one question. Because if you don't, then just get more data and be happy. Simple solution. Things get interesting as soon as you have a good argument for saying that no amount of data would be enough. I think that's a really interesting thing. I don't know that I have perfected any argument to that, but I think there probably is such an argument to be made that, like, no amount of getting the data can tell you what's outside it. There could be black holes lurking exactly beyond everything that you've sampled. You can't guarantee that that's not the case, no matter how much you collect. So that's one thing. So I think that's already a very interesting thing. If you can show at least the inadequacy of going out there and collecting data in a fundamental way, doesn't matter how much you collect. So that's already interesting. So that tells you you need something else. So yeah, that's the first level, which is interesting. And then you can ask, what else is there besides data? And now you're kind of, the real answer is everything. There are many things, all kinds of rule-like ideas you can have, things that aren't measurements, whatever. There's an infinite variety of types of knowledge that might exist out there, intuitions and rules and other things. And so you can just say, okay, these are supplementary things that you might want to bring to bear. And by the way, from a Popperian perspective, talking about rules and so on as like supplements to the data already sort of has it backwards. That's Popperians don't still look at the data as the main thing and then have other theories as the side piece. They look at the theories as the main thing. But anyway, for somebody interested in kind of the neural network training world, who sees the data as primary, this is interesting kind of perspective. So I always like to thinking about, what are the strengths and weaknesses of data? What are the limits beyond which it can't go? I think that's one way of kind of speaking to the modern machine learning world.
Yeah, I think depending on how you define things, like one way of framing it, you can always just say that data is all you need, especially if you're training on like scientific knowledge, because anything you could come up with, say, without data, if you just had that as part of your data set originally, you could kind of learn that, right? I don't know if I'm making sense, but if you kind of define data as anything that you want to have, any kind of program you want to run, and your data is also programs that you are learning from, then it's almost by definition you can say that, in this magical world where you can summon all the data you need, you can summon whatever. So it's kind of it's almost like not well defined, or like nonsensical as a thought experiment, because that world doesn't exist. And that's, I think, where things get interesting, and where the more interesting parts and like discussions in machine learning are, I think, going to happen now. Like, I don't know if this has crossed your timeline yet, but there are these open math problems called Erdos problems that GPT 5.2 has solved like one or two of them recently. And the mathematician, the famous guy, Terence Tao, has been commenting on that as like, these are impressive things. So far, it's this interesting thing of like, it's relying on the human knowledge in the training data, but then I guess the word I would use is like, there's just so much horsepower, like you can run the model for so long and just have it generate all sorts of stuff that you can then verify, check, write code for to see if it solves the problem or it doesn't, that you have like some of these open problems that you can just kind of like find answers for.
It seems like you're making a distinction between like all current data that we have and then all possible data,
Yeah,
possible ever, that you could ever have. And I
yeah,
guess you're saying that if we collect all current data, we still can solve some new problems, right? Like those math problems that you're describing. And they seem like novel solutions. Is that right?
Sorry, still can or cannot solve the math problems.
They can. Like if we have all current possible data, they can solve
Yeah,
some problems, some novel
yeah,
problems or problems that we didn't know we had the solution for or something like that.
yeah. It's the way I would describe it is like you have a circle that's always growing of human knowledge as we collect it, but then once LLMs come about, stuff that's like on the edge where it's like not figured out yet because no one had the time, but the knowledge is kind of lying around, that if you tried a bunch of stuff and then had some verification system to confirm if what you tried worked or not, there's a bunch of stuff around the edge that you can kind of just like get at.
Seems
But
like, thinking about it, like it has some idea of intuition, uh, where it kind of knows what is the direction to head. And if you have enough of it that it's actually useful, you can kind of swap it with processing speed, where it's like these things are potentially worth trying and you can try them all quickly. Or maybe if you have better intuition,
Yeah.
you could narrow it down and have fewer things that
Yeah.
you need to try to find it. But I guess somehow the model has learned enough to figure out how to head in the right direction. It's not just like manipulating theorems to generate new theorems in hopes that it'll randomly lead somewhere
Right.
interesting.
Yeah, I think it's a balance of both of those things where on the one hand, you need a model that's good enough that is not going to just generate garbage. But then even with a model that is quote unquote good enough, you need to be able to run it for quite a long time because even then, even being good enough, it needs like time to think and work out stuff that goes nowhere. And then eventually you find the solution.
This is where I like to think about that picture of the sort of the faucet and the filters,
Yeah.
because you can ask about the quality of each of those components. And in this case, one question you can ask is, or you can ask those two questions I raised before: could the system produce a certain thing? Could it reach it? And secondly, how quickly, with what effort and resources? And one variable you can look at there is like how wide is the initial sort of expanding funnel? How wide is the faucet, the shower head? Can it even produce? Is it even trying the relevant things, or is it too narrow? And among the things it's trying, what fraction of them are reasonably good? Because is it just generating huge amounts of garbage where like it's 1 in a trillion are even reasonable, or is it 1 in 10? Okay, that's a big difference. And then likewise, how good is the sieve and filters? Are they really quite sophisticated and sensitive, where they only let through the good stuff, and they are able to kind of separate the good from the bad quickly, or do they get clogged up and they're not very efficient, or they're pretty non-specific, so they let through a lot of bad stuff, or are they so stringent that they let through almost nothing? These are the kinds of questions that I think become more intuitive to ask about any search processes when you have that sort of visual of the faucet and the filters.
Yeah. One thing that I think is interesting to point out that I think about is that like the selection processes, there's definitely two groups of them. Like one of the selection processes is like trying to compile the lean code for your math proof and seeing if it compiles or not, or judging your own output and being like, did what I just say make sense? Like, let me double check. Like you can put the prompt of like, let me double check after the LLM's output, and it'll kind of check its own work, which is like kind of this explicit thing where you can read out what was happening in the logs of what the LLM was saying. But I think then the more interesting selection criteria is like in the forward pass of the LLM when it produces a single output or a single token, where the majority of all the tokens are going to be low probability for any one given answer. But there's a reason for that, right? Like as the forward pass was happening, and like if the sentence was like, the capital of France is, and then all sorts of words like chair and towel are being like lowered in their probability as the possible output, and that has to be, as we all know, like some kind of selection process, whether it's like some competition or something less like competition, something else, which I think is more interesting and just like the thing we have like very little insight into as to like how to. I mean, there's some insight, but even I'm not like up to the cutting edge and all this interpretability stuff that like Anthropic does, where you would be able to characterize, how that selection process is happening. But I think like I think right now everyone's going full pedal to the metal with like all these agent orchestration things where you can work to make the selection process better for the first group that I pointed out, where it's like the output and the logs, and you like, for example, have a LLM define a subtask and then launch a new LLM to go do that subtask, and then it comes back and you check with another LLM whether it did it, like that kind of thing. I think there's crazy progress being made. But the the second more interesting one, in my opinion, other than like, scaling on a bigger data set with a bigger model, I think it's just not clear how we would improve that or even gain any insight into it. Which I just think is interesting. Like if we ever figure out how to like go in there, with a hammer and a wrench and like manually improve things as opposed to like piling more data on the mountain of data or more compute on the mountain of compute, that'll be, I think, just a super interesting like whole field of like, oh yeah, what the hell is going on? Yeah.
Well, I think one take on that is the idea of thinking about, what I talked about before as attention, and where ideally you know many things, but you're bringing to bear those few that actually matter in the next decision. And so in the forward pass, you're saying, hey, here's the context we have.
Right.
And you're looking for a solution to something. Ideally, you would mention something relevant. But what are your criteria of relevance? How are you assessing that? Why is the forward pass doing that? I think one version of that, by the way, is just recommendation algorithms in general. And you're sort of saying, hey, there's a lot of stuff I could show you. So which few things should I show you? And that's as true for Netflix as it is for X. I'm going to show you 50 posts in your next timeline refresh, and your own mind, where it's like, hey, we're in a conversation right now. We're talking about X, Y, and Z. If I'm going to talk, what do I want to say? When should I even say anything? And when does an idea come up that, this is worth saying, and I'm going to say it in this way? These are all sort of the same problem on some level. And I think where the sophistication and kind of the fun part to think about here is that there are all kinds of ways you could assess relevance. And really, it's not even about relevance. It's kind of about like fruitfulness or whatever you should say next. Because sometimes the thing that you should say next is something that sounds to everybody else completely irrelevant, but unbeknownst to them, it's extremely relevant. And so it's not about matching existing notions of topical similarity or something. It's about saying, hey, in fact, the most useful thing you can say usually is the thing that nobody else knows, but is in fact exactly the thing that they should be talking about. So what kind of process would serve that up as a recommendation is kind of an interesting question. And that's, again, not about topical similarity necessarily.
Yeah. Just another cool analogy. Sorry, I'm like in this rabbit hole now, and I have many thoughts. There's a I think an analogy between like the knowledge that is stored in genes as opposed to the brain or the mind for like even say a bird building nests, right? Or like let's say a zebra that injures its foot and then it has to learn how to walk with a limp. There's clearly like some adjustment process as it learns how to like not put pressure on the hurt foot, or the bird building a nest and I don't know, some branches are wet and so on, where the adjustment or the details are stored in the brain and not in the genome for that particular thing. There's an analogy between that and the training process versus inference process of an LLM doing something. So what I mean is that during training, it learns how to associate certain words with vectors that will capture the properties of that word, like apple and orange. But then remember, I don't know, a few of these conversations back, I did an experiment where I said like, I'm redefining dog to mean cat and cat to mean dog, and now please describe a dog for me. And then I was still able to do it. So it's similar to how in certain cases an organism has to maybe rely more than it previously had to on some new knowledge that's only in its brain because it's in a situation that is unusual compared to its typical habitat, let's say because of whatever reason it's hurt its foot, different environment, super harsh winter, whatever have you. The LLM will also be in certain situations sometimes where it has to rely extra hard on what the ML people call in-context learning, which is that like the information processing is you only know the relevant stuff because of your current context, and it might even be the opposite, literally, compared to what it was during your training data. So you really have to focus on the context and like ignore the training data. Anyway, just I think there's like some parallel there that might be deep, but I'm not sure.
Interesting. I know there's like some work on kind of showing that it's almost the same as like changing the weights when you prompt it a certain way or something.
Yeah, that sounds familiar. I am not familiar with it, but that's something I might want to look into. Yeah.
Yeah. I think, one thing that sometimes I think about, which is a somewhat, maybe different, maybe related issue, is that when you talk about knowledge creation, you could say, okay, if you're looking at a system and asking how it generates knowledge, you could say, where is the variation happening? Where is the selection happening?
Right.
You talk about the forward pass. It's doing some kind of choosing what's relevant and so on. There's some kind of selection happening there, you might say. And so one kind of question that comes up when thinking about the power of LLMs is that if you constrain yourself to looking at them very narrowly as just the forward pass, you'd say, hey, there's only a limited amount that it can do in one pass. So it's pretty limited. And then somebody will say, well, you don't have to do it like that. You can run it in a loop. I'd say, okay, that's cool. But okay, now you have to run the forward pass, store something, run it in a loop, read what you wrote, go again. And so, okay, you have this looping process that is now less bounded than before. But now you're engaging in a process which is not like the training process. The training process is guided by gradients and all this, changing the weights. So what is the relationship between these two loops? And if you're looking at the power of an LLM and saying, hey, you can train LLMs to be so powerful, I say, great, but is that what you're doing now when you run it in a loop, when it just has the in-context thing going? What is the power of that process? Is it, can you keep that going forever and it's just going to improve some kind of loss function, or, is it going to get better in any measurable sense? So that loop is a different kind of loop. So it's just interesting to wonder about the power of each of those two loops.
Yeah. One just interesting thing off the top of my head is like the second loop at the very least is generating a data set or the raw materials for a data set to like improve the data set that the next year's LLM will be trained on, or maybe I should say next month's LLM will be trained on. Because, I'm sure they're doing this where it's like you have a long Stack Overflow type thread of like someone debugging the thing, and you can basically use an LLM to filter over it and be like, hey, this user went through like 3 different chats before finding the root cause, but the root cause should have been known initially, like instead of this swirling thing. So make a little thing that we should put in our data set that correctly solves the problem on the first try. And but I think your question is like interesting of like, okay, other than that very like brute force type thing, can we have any like virtuous cycle type process of learning from inference as opposed to just training? Which I don't have a good answer to, but it's a cool question.
I think it's cool just to model that in terms of the faucets and filters and say, where are the faucets, where are the filters, and say, okay, cool. In that case, you said, if you run the LLM and it eventually produces a good answer, and you as an LLM product designer decide you want that answer to be produced more quickly next time, then you can ask, okay, where were all the decisions in this process made? You eventually found the right answer. How did you know that was the right answer? Is one question. Is it because the human did something? Okay, how could you bring that into the loop? Okay, and then you could say, well, how are you coming to the conclusion that the previous steps that were tried should not be tried in the future? So what if that is the right way to try it?
Right.
What if there was like a really weird bug that is never going to occur again in the history of humanity? You don't want everybody to look for that bug first in the future. That's a waste of everybody's time.
Right.
So yeah, how did you make that calculation? And on and on. And I think so that's kind of interesting. So I think it's a fun, speaking of what should be reflexive and moved up in one's reasoning, I think that thinking in terms of faucets and filters is a fun thing. But then also I think, what was I going to say? But also a side quest from all of that is just saying, isn't it fun to look at any given process and ask where all the knowledge and knowledge creation was? Because we usually don't do that. And, as a person who worked on robotics at one point, every time I go up the stairs, I'd say, wow, I'm walking up the stairs, and why can't I make the robot do that? And you're thinking about where all the knowledge involved in taking each step is. And so likewise here, it's just a fun and I think often overlooked thing to say, hey, here's a thing that's happening. Let's actually take a pen and walk through all the decisions that were made, all the intuitions which were deployed, all the things that happened in a human mind or in a computer program or in the LLM. Where did the thing, what happened? Where did it happen? In what system did it happen?
Mm-hmm.
Just get really good at knowledge accounting.
I'm thinking about Lamarckism again for whatever reason. I just like Lamarckism, but there's a similar issue with that of if you have knowledge in memes, that doesn't directly translate to genes, right? And if you don't have the distinction of the different types of knowledge, then you can't understand why learned behaviors don't automatically get put into genes, or why they can't at all be put into genes. And that being the reason why those what do you call them? Phenotypes? I don't know what they call it. Those things can't be.
I don't know why that sounded racist to me.
Phenotypes?
Just you say, what do you call them? Phenotypes?
What do you call them things? Phenotypes? Yeah, but those can't be passed on to the offspring directly. They have to relearn them. And it's because it's not in the DNA.
Total side point, by the way, as long as we're talking about DNA, it has me thinking about DNA computing and just, DNA as a programming language, DNA as a hard drive, just thinking of it purely, maybe abstracting away from the biological context. And, if somebody just says, hey, I invented a way of doing computing, and they show you DNA, it's interesting to think about what's going on there. Is that a cool thing? If it was invented today, would people like it? Would there be advantages to using it? I've seen a couple lectures on it a while back that I vaguely recall, and they just said, the name of the game is that you don't have access to a Turing machine that can run everything in sequence and this kind of stuff. So when you think about how to work with DNA, it's all about matching strings. And so you have to produce a string, and if you want it to be somehow associated with some other thing, you can't just say, go to position 1, 2, 3 and do this thing. You have to say, go to a place that matches A, T, T, T. And then you're going to have your buddy there. And then because the chemicals can combine with each other, then the right sequences match up. Okay, now you can specify a location, and you can say, hey, these two things need to combine here. But you have to specify that in terms of matches of strings. And you can do weird things with it, apparently. It's a little bit like quantum computing, maybe in the sense that not everything, there isn't maybe a direct way to convert one algorithm that's classical into a quantum one in a way that is helpful at all, or is an improvement. I think likewise with DNA computing, it isn't the case that you can just speed up everything by doing it. However, it's kind of just this different programming language with a different substrate. So if what you want to do is do a search process where you can just produce a whole bunch of candidate solutions, and then just say the right solution will match the string here. So I'm just going to, how to describe it? You can just have all the wrong answers and the hidden right answer bouncing around in this liquid, and then whichever one is the right answer will just combine with your search query, which you drop in as another drop of liquid. And then you just say, hey, who did my search query link up with? And then you just suck it back out again. And then you say, okay, that's the thing that connected to that. So cool. So you've run this parallel search just by literally like bumping all the molecules together within a liquid. And depending on what the problem is, maybe that's actually pretty fast. And then you can like serialize that and have a process which kind of does this kind of thing again and again, again and again and again to make a longer algorithm. Anyway, that's my vaguely, very shittily recalled DNA computing thing, which is kind of interesting to wonder about.
The way I'm thinking about that is just that you can't index it abstractly. Is that you can't like abstractly put, this is in position 0, this is in position 1, this is in position 2.
Yeah.
Is that right?
But even in like existing DNA, like in the way that like regulation of like gene regulation works normally, is you kind of have this gene over here, and once it gets like transcribed and it's like moving around the cell, then it's like hooking up with another part of the DNA and saying, hey, I want you to open up and start producing more of you. And then on it goes, with this triggering that. And they can correctly trigger the right spots because of the matching strings. So it's interesting, just that framework. And it can go to, it's almost like a random access memory. It doesn't specify a location, but it does specify sort of it's like, matching, it's just matching. So I guess it's like maybe content addressable memory, sort of.
Mm-hmm. Interesting. And do you know a lot about, I mean, you seem to know a lot, but
Oh boy, thank you. I know all about what is it, the rats and what they do.
Yes, having sex in the
More than I
woods.
would like.
Yeah. But particularly, I just don't understand this portion. What does the matching do? Like if there's a sequence and then there's a floating protein, I guess. I don't know really, but then they match. Does that do something? Is that like the matching itself something?
Yeah, I actually know very little about the thing, but
Okay.
but yeah, a lot of what happens is you have, A's connect with T's, right? And the C's connect with the G's, I
Oh,
think.
gotcha. Okay.
So those are complementary things. And so, that works in both how you just store a DNA strand at rest, so you have those two strands that are complementary. But then, and then when you read from it, you open up that strand and you produce a complementary string. So if it's an A, then you connect a T to it. And so that's how you copy it. So anyway, that's just the general framework in which you interact with DNA, is by making these complementary pairs.
But then what is the function with, like, when you have a particular, sequence A, T, C or whatever, and then is there like a uniform function, or is it always the same? Is it?
Well, I think part of what happens is that you produce like a long string, and just like the first part of it is like a search query. And so it's like, hey, I want to match with this thing, and then these two things will match. But also the search thing that you have has a whole bunch of other stuff on the end of it. So you're not working purely with the search part. It's like the search is attached to something else. Like maybe it's almost like a light bulb type thing, like some other molecules attached to it that will like blink if something matches with it, kind of. That's again, a shitty recollection, but
okay, yeah.
But the key idea is that you sort of have matching, and you have things which are attached. You can attach all kinds of stuff to the DNA, and you can just match to certain subsections of it. So it's almost like match-based computing, whenever you can frame something in terms of matches of strings. And yeah. Anyway.
Interesting. Yeah, interesting.
I just thought that DNA is like this weird thing, and I think perhaps the main point that I'm making is like it's just an interesting programming language almost to think about, that just operates in a very different way from the usual things. So it's a head twister.
And are there particular programs that are more efficient in DNA computing, or that you know of?
I think so. But yeah, it evades my recollection what they are. But with any kind of like weird substrate, you can maybe, it's got to be helpful for something, one would imagine. That's kind of what people are working on, by the way, with like neural network things. Like some people are working on hardware that is supposed to like natively deal with like distributions and stuff like that. And so if neural networks really love and are on some level about working with distributions, then a hardware that does that efficiently at the lowest level might be very good. And so I think that's one area of research.
But, I feel like I asked this before, but maybe you have a quick answer to it. Can we given universality, if we have any program, can we make it arbitrarily more efficient? Or is there like a limit to some programs in some particular hardware, a limit to their efficiency?
Say that one more time.
Can we, like using Turing machines, become arbitrarily efficient at any program?
Oh, well, I maybe a computer scientist that should answer that, but at the very least, you can say if you're looking at the level of physics, that's a question for a physicist. In terms of like how is it possible to use arbitrarily small amounts of energy to produce that computation? There's a separate question about like, can you make that search algorithm more efficient, ignoring the energy requirements? All you care about is like, I assigned this variable, I multiplied this number. I'm not worried about the physics involved. I'm just worried about how many computational steps I took. And at that point, there's probably proofs out there that say, hey, like you can't multiply any faster than this complexity class. So that may be a computer science type question. Although, by the way, David Deutsch would say like you probably can't answer those types of questions without looking at physics, because it's like a computer scientist might say there is no way to perform blah 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 faster, and then he invents the quantum computer, which lets you make use of parallel universes. Suddenly, okay, your existing complexity classes do not. I never conceived of that possibility of using the universe in that way to perform that calculation. And so there's more resources available, and actually, yeah, you can do that thing more quickly than you thought you could. But yeah.
Yeah, one just concrete example is like sorting a list. Once you have a theory of computation, and yeah, like what Carlos said, if your theory of computation changes, then yeah, it's Wild West again. But for example, if you're sorting a list, you at the very least have to look at each element once. So if you have n elements in your list, you can say a lower bound would be at least like big O of n. Big O is just the notation we use for what's called time complexity. And then there's a proof basically for comparison-based sorting. The lower bound is n log n, meaning that you will never get better than n log n. But there's a lot of like complicated probability theory that gets involved, because like you might get lucky where your list is already almost sorted, so you just have to change one thing. But other times your list might be totally garbled, so then you have to like think about it with uncertainty and stuff. But there's definitely lower bounds for the efficiency of not algorithms, like problems. So like sorting a list, regardless of the algorithm, you can prove that regardless of algorithm, n log n is like for comparison-based sorting is as close as you can get.
Interesting. Is there like a name for that? Like, I guess you said problem, I guess it's a class of algorithms. Is that, I don't know, but is there like a official computer science name for that type of thing?
I guess task, but I'm not sure.
Task.
It's been too long.
Okay, cool.
Well, nice. I think we'll call it there, and I just got a couple of phrases I want to share that I made note of throughout the conversation here. So this will be our wrap up here. So we got knowledge accounting, looking at all the knowledge in a system and that kind of thing. I like a phrase that if I come up with something I haven't said before, then I try to make a note of that put that in the book. We had faucets and filters. Let's try mapping that onto any situation where knowledge creation is happening. And then lastly, I'll just end with my new favorite quote. I doubt your response could have been produced by rodents randomly breeding each other in the woods.
Nice.
So with that, until next week.
See you next week.
Bye bye.
Yes.